Okay, well, thank you so much for the opportunity. This is fantastic. So I'm going to dive right into this. Well, most of you guys have done a lot of work in the past 15, 20 years, but I want to maybe focus a little bit more on the research that you've done, but you're more than welcome to go back to the roots of it and beginnings of them. So I don't know how to start or which one to go first, but I just put like the top high level question. I want to talk about your network level traffic flow research. Okay, so how did it started? Why it was even needed at the time that it was started, and then how it progressed to the point that where we are now. Who wants to take that first one?
Okay. So I personally, when I started my PhD, I was eager to deal with large-scale stuff, and we had the opportunity back then in 2005 for access to a unique data set that was provided to us by Professor Kuwahara from Japan. That were about 500 loop detectors from a city in Japan, in Yokohama, and about 150 taxis with timestamps. And by looking at this, we were able to observe some network-level relationships that experienced much less noise, even for different demand profiles, than the classical loop detector point data for the fundamental diagram. So we named this the macroscopic fundamental diagram. Other colleagues call it network fundamental diagram. It doesn't matter the term. And when I was searching the literature, there were also other nice works. The first one goes back, I think, to 1969 by Godfrey. That was the first one mentioning and also observing some type of MFD with real data. And then you have the two-fluid model by Herman and Prigozhin that had some features of network aspects. And later was Hani Mamasani's group that looked in some static relationship with static simulations over 30 minutes and also saw some network level relations. So obviously there are more people and more papers, so maybe we don't have the time to mention everything. So observing this network level relations, it doesn't mean that this applies to every network and every time and space aggregation. So there was a lot of research, let's say in the last 10, 15 years to see under what conditions MFD is a valid relationship at the network level. And then there was effort to extend this to multimodal systems and also utilize this for traffic control. And recently in the last, let's say around 5 years, we also see efforts of MFDs in different type of systems like on-demand transportation, etc. So I believe we will have time to discuss each of these as we move forward, but I believe this is a nice introduction.
Yeah, I just want to share first a personal experience, because at the beginning of my career, I was doing traffic flow theory, but more the classical one. So everything related to car following, congestion spreading and everything. And basically I started building up from very local problem like car following, multi-lanes, intersections. But at one point I was trying to address large-scale problem, especially large-scale urban problem. And this is when I start being aware about the work that Nicolas did about the macroscopic fundamental diagram. And I was very, very interested in the application for modeling and simulation. Because like the regular fundamental diagram, it gives you basically the basic of expressing all the transportation system with a simple conservation equations. And based on this equation, you can look at the dynamic of the system. And I think this is really the strength of the macroscopic fundamental diagram, because it gives you access to the dynamic at large scale, and then you have a lot of potential application for many transportation problem, control, obviously, and for example, the work on perimeter control is really driven by what has been learned from the macroscopic fundamental diagram, but also many other kind of application, multimodal traffic, on-demand mobility, everything related to urban large scale. And I think that this concept of macroscopic fundamental diagram is really the one that help keeping the dynamic of the system while being able to address very large scale problem, because scaling up microscopic model or even the classical macroscopic model at the human level was going nowhere in terms of application, especially if you want to couple this with optimization problem like we like to do in control.
Okay, that's a very interesting point. So, well, in some of your more recent studies, both of you have talked about essentially a trade-off between just what you mentioned, what you're gaining by going at the larger scale and network and doing aggregate work versus what you're missing, and how do you balance between essentially the being able to handle larger scale data versus missing a lot of local dynamics? Would that be even a factor that you would consider that, okay, this is something that we really have to deal with in order to take this research to the next level? Or it is really just can be considered just sort of a noise in the system?
I mean, again, starting from the past, there used to be this kind of dichotomy between static model, where you had very advanced representation of individuals through generalized coests. So there is a lot of characterization of the variability of individuals, while the traffic representation was so simple that it was not able to really address the simple question of congestions. So when you were doing planning over long terms in a system where basically the idea was simply to add capacity where it was needed, it doesn't matter. But now if you want to look at the human system, transportation system, and the fact that we cannot build roads everywhere, we really have to handle congestions and consider congestions as a core feature of the model, then we really need to have something that still includes some individual characteristics, especially for the trips, but that can capture better the congestion. And I think this is something that's some variation of the MFD theory, and especially the trip-based approach, where you look at trips of individuals while having this global dynamics through the mean speed given by the MFD, is really appealing, because you have kind of the best of two worlds, because you can still look at large-scale problem, look at the level of details you want for individuals in terms of behaviors and especially of choices, also in terms of management of some component of the system, like the fleets or on-demand mobility services or whatever you want to consider. It can be integer, while having something which is tractable and that you can really use in terms of simulation. So this is, I think, very important features of these works.
Great. So if I could add to what Ludovic mentioned, I believe the model we're interested in and we're looking at and we're developing it also depends on what is the final product and the research question. So we cannot, each model has pros and cons, and clearly is an abstraction of the real world. So clearly we cannot utilize MFD if we're interested to do microanalysis of traffic behavior. But network level modeling can be useful if we would like to answer questions, so how to do large scale control where local information and local decisions might not be sufficient for the system. Or even worse, local decisions that you can make by utilizing local information can create negative impacts at the network level. So, would you like to talk a little bit about network control, or would you?
We can move to. I mean, you guys have done a lot of work on the network control now, and we can jump right into it. I just have one quick question before we move from this. So, what you mentioned is essentially optimizing a small piece without having a big picture can be actually bad idea in general. But has there any work in reversing this process from a sense that, things like wavelet transformer design, to be able to be reversible? And you simplify the signal, but they can revert back and recreate the original one to some level. Has there any work done at this sort of aggregation to be able to recreate either the link level information or the trip information based on what you observe at an FD?
Actually, it's a good question. We just finished a paper together with Ludovic and one of the students who are co-supervising, that by using some machine learning techniques, we try to see if we can train a macroscopic model to reproduce microscopic features, and the answer is positive under some circumstances. So clearly, such an approach cannot replace a detailed dynamic assignment model, but it can give quick and quite accurate answers even if demand profile changes, because there is some repetitive aspects and some spatial correlations how congestion grows and propagates. So we look for feedback from reviewers, but this was a first effort of the reversible problem, and their modeling might not be so easy, and machine learning is a strong tool that can help to answer this type of questions.
Well, I'm not a reviewer on that paper, so I didn't know.
Yeah, if I can add one thing, I mean, what is very important to understand is that when we speak about network modeling, we cannot address very local problem. For example, if you have a bridge, and then suddenly this bridge is not available for any reasons, I mean, network modeling will not be able to see the impact of this very local bottleneck and how it's spread on the network and what is happening. So you really need a local approach for local problem. But in your questions, I mean, local doesn't mean that it's local, it's maybe simply heterogeneous. For example, and what we did with our joint PhD students is that when you have dedicated bus lanes or you have lane reduction on some link, we know that the speed will be different from the classical configuration when you have two lanes. So while the MFD theory will tell you that in these regions you will have this common average speed, you know that by the network configuration there is some corridors or links where the speed will be lower and some when it will be higher based on the configuration. So this is local heterogeneity. And this local heterogeneity can be characterized, and this is what we call the local correction factors, meaning that we know what is the average speed related to the average level of congestion, but then we will consider some local characteristic related to the configuration to adjust the speed and have a better description of what is happening locally. So this is really something that I think is consistent with the network modeling. Every time we have local heterogeneity, and we discuss, for example, clustering, or what it means to look at heterogeneities, and we can handle heterogeneity in the system. But everything which is very local and specific bottlenecks or very heavy singular point is something which is definitely outside the area of validity of network modeling.
So, so this fits, from my perspective at least, right into the optimization part. So, in order to be able to have some sort of congestion management using this, do you need to know which links are more important than the other ones, or you treat the whole thing as kind of like uniform?
So here, I believe one, let's not necessarily call it breakthrough, but an important feature of network control, and Ludovic mentioned this word, is clustering. So transportation networks is by nature heterogeneous. And if you want to minimize your heterogeneity, your number of clusters would be equal to the number of links, or even a smaller resolution, because if you have a link, maybe the front has a queue and the back of the link is free flow. So the idea is how you can take a network and divide it in a small number of regions, that this can still give you a dynamic representation of congestion. And what we have seen is that you don't need to divide your network in too many regions if your objective, for example, is large-scale perimeter control. Or if we talk later for on-demand transportation, which might be rebalancing vehicles without passengers from one region to another. So clustering really gives you the power to revisit network level models and really deal with traffic control strategies. Because if we look, for example, the idea of perimeter control or gating is not news. I mean, RAB metering is around maybe for 40, 50 years with many different studies and implementations around the world. But urban networks have also different complexities compared to freeway networks. But they also have something better, which is the redundancy in terms of topology. Meaning that if to go from point A to point B, you have many options. This helps the network to be locally heterogeneous, but to observe at the big picture, like if you go at a higher level, some aggregated homogeneity. And this is why clustering can help. And then based on this, you can extend or look at control strategies that build on simple concept, as I mentioned, RAB metering, or for example, the single region perimeter control that Carlos D'Aganzo introduced in the beginning back in 2007. And we can discuss more about multi-region stuff, but in terms of modeling, I believe clustering is an important step. If I would like to summarize, there are different clustering approaches in the literature. And while when you use clustering, you need to formulate this as an optimization problem with an objective function, etc., my personal opinion is that clustering is not as crucial with respect to control. Meaning that small deviations, it doesn't mean that there is a best clustering technique that minimizes the total heterogeneity of the city. So different clusters, even simple ones, can give you a good flavor where is the main pockets of congestion. And then if you apply the same approaches, either in modeling or in control at the regional level with a number of regions, you can get significantly better results than the single region.
Yeah, I mean, if you think about urban traffic control, I mean, the main tools we have is traffic signals. And these have been, work on for, decades and decades. And I think what the network modeling approach brings to the table is the opportunity to change the scale, because everyone knows that optimizing taking all the signals and looking at the problem like I want to have the optimal signal settings for all my signal in a real city. I mean, it's not possible to solve this problem. It's too big. So the classical method was to look at some corridors, to make some coordination between local intersection and so on. But by doing that, you improve, for sure, but you are missing the big picture. And the big picture is that the demands come all around the city in certain directions and create congestion, pocket of congestions in some specific areas. And what Nicola mentions about clustering, it's just something that will help you to identify where are the global congestion problem you may have at the city level. And when you know that, you immediately see that gating helps you to avoid oversaturation regime, where we all know that if we have too much vehicles, basically the outflow will decrease and we will lose a lot of optimality on the network compared to what is possible. So, clustering is the first step. Then perimeter control is the second step, but all this is possible because we are able to identify where are the global problem and provide global solutions. So now you may ask, okay, I have a city, I want to implement perimeter control, I want to know where to put the perimeters. Again, the clustering helps to do that. You also have, traffic engineers know also where are the congestions. But what is important is that perimeter control gives you a kind of coordinations of signals all together in one very simple shot. And this is the beauty of network modeling and network control, is to be able to scale the problem and identify some global pattern at the city level that you can try to tackle. And of course, then you can have coordination between network control, local control, just to ensure that everything works efficiently. But you can do a lot of things. Just another element, because we often see perimeter control as just like a cordon around the city centers where you control. But you can think about more advanced application of perimeter control. For example, if you have a bus line and you want to improve the quality of service for the buses, every intersection, when you have signals, can create a virtual cordon around the bus line that you can just try to monitor through perimeter control theory, and just to improve what will be the traffic condition inside these regions. So there are many things you can do just by looking at the traffic problem at the network level.
I have a weird question. So I remember there were some studies that were focused on figuring out if the network level relationships are a characteristics of the network, or they are related to the traffic flow dynamics, or they're not. I'm not sure where that line of research ended up eventually, but would what you're talking about in terms of perimeter control or clustering impact the shape of dynamics at the network level?
So you mean if perimeter control influences the shape of the MFD?
Right.
So if we look at the MFD of the whole city, when you intervene in the traffic lights inside, then the shape of the MFD can change. And there were some studies back in 2008, and then we have a paper with Ludovic, I think 2011, where you can also use variational theory to address this also from a theoretical point of view. But if you are careful on how you do your clustering, and you mainly control the intertransfers between boundary regions, and you also try to apply some smoothing in these boundaries, then you might not change significantly anyways. The shape of the MFD has some stochastics and some uncertainty. You might not significantly change the shape of the MFD, but if you do proper control, you can move into less congested points in your MFD for the different regions. So that's the reason when you apply perimeter control, you have to be a little bit careful which traffic signals you choose. But if you combine upper level perimeter control with lower level controllers, so for example, you apply max pressure in some traffic lights, etc., compared to fixed time, then indeed you can influence the shape of the MFD in each region.
Just an addition on that. I mean, the seminal paper, I mean, the beginning of the MFD theory, I mean, there was this idea that the MFD only depend on the network, so the supply side. I mean, now we have 15, 20 years of experience with the MFD. We know that the MFD shapes depend on basically everything. Everything means the traffic control inside the regions, the routing inside the regions, the demands. So then you can say, okay, but if it depends on everything, I mean, does it still make sense? And this is certainly one of the studies that is, for me, on one hand, surprising, but on the other hand, it's the beauty of the MFD concept. When you start looking at, on real data, the repeatability of the MFD, so you look at MFD shape for many days, let's say 1 year for the same cities, and you do clustering. And it's interesting because we discuss spatial clustering, but you can also do temporal clustering for one regions. What do you see? You usually see that with 3, 4, 5 MFD shape, you can basically represent every situation that a city have experienced over a year. Why? Because the demand pattern doesn't change that much. The routing doesn't change that much. The control, I mean, change, but not that much. So in the end, the MFD is a strong concept to characterize how the system behaves. And if you have very different situation, like for example, I mean, holiday seasons versus weekday periods, then maybe you need 2 MFD. But if you look into the details, I mean, the free flow power will be the same. So the saturation level, not that different. You may not reach the saturation, but not that different. So you will see simply a little bit of shift in the saturation regions. So, okay, so maybe you have to adjust a little bit your control parameters if you want to make it very, very adapted to the actual situation. But still, I mean, the key elements of the MFD are there. And this is why you can develop robust control applications, because in the end, the demand and the routing doesn't change that much at the city level. So when you know the combination of the supply and the demand for a particular city, you have a strong leads towards a more efficient system.
I want to ask a question about the importance of like sort of a comparison between a unimodal network relationship and a multimodal network relationship. I know you've done some studies recently on this, but how important that is from a control perspective, or it really doesn't matter really based on your experience?
Okay, I mean, I can start on this one. I mean, the multimodal MFD is really useful when you consider mixed lane where car and buses. Because depending on the number of buses operating and the level of interaction between car and buses, and we all know about the moving bottleneck theory from Carlos, and we know that when buses interact with car and change the overall flow. So this is exactly the same thing at the network level. I mean, and this is something that you need to consider for managing both car and buses, because if you have more buses, that means you may certainly need to reduce the inflow for perimeter control, just to ensure that the system is working at the optimal level depending on the number of buses. So the multimodal MFD is not necessary for all application, but for some application, it's really improve the quality of the results.
And if I could add, once we move from unimodal to multimodal, you start adding complexity in the network. And what you have that different modes interact and influence each other in different ways in different parts of the network. So it might be more challenging to integrate these multimodal network representations in real-time control. This might help you to make planning decisions. So, for example, how to redistribute urban space between cars and buses. Or possibly, we published a paper recently with Lyon, one of my PhD students, and Gustave, a postdoc in the team. If you want to allow some types of vehicles that in that case might be ride sharing, so that are carrying more than 2 passengers, to use the bus lane. But perimeter control gets more challenging, and I believe in multimodal networks you might need to combine the upper level perimeter control with other type of lower level strategies.
Okay, but would that then impact, that would impact the outcome of your clustering, right? So as you apply different types of control at different levels, would that impact your clustering, or you do the clustering at one step, you keep it constant, and then you apply everything?
Look, I think that you can recluster if needed. And actually, if we go back, why we needed clustering? We needed clustering because the whole city is heterogeneous. So if you have a heterogeneity index, this heterogeneity index can treat when you need reclustering. And if you have multimodal networks, you might have a multimodal heterogeneity index. So you come up with some initial clustering. It can be based on historical data, or it can be in the real data of the last hour. And as you move forward and you continue to have real data, you reevaluate. And if you see that you become very heterogeneous, it might mean that your aggregated control strategies are not performing well anymore, and you need a new cluster before you continue. But what I would say is that the dynamics of reclustering are much smoother compared with the dynamics of control. Because if we do perimeter control, probably we'll have to do every 1 or 2 cycles period, while if you do clustering, maybe you have to do it every 5-10 cycles, depending on how the dynamics of the network change.
And if I may, just one addition. I mean, we are a lot about control, but MFD and multimodal MFD can be also very useful for simulation. And now, let's say that you want to investigate a urban multimodal transportation system at full scale, and you want to see what's happened if you had some bus lane, you want to introduce some on-demand services. What you really need is something that will give you good estimation of travel times for each mode of transportation, so you can couple this traffic flow dynamics with a choice model that help you define what are going to be the alternative chosen by the users in the system, so you know the load and you can basically loop the system. And if you think about it, I mean, a good estimation of travel time over a trip, it's just having a good estimation of the integral of the speed over a certain time. And this is where having multimodal MFD function is very useful, because it gives you good estimates not of the speed of each individuals, but the speed of the users that are currently in these specific regions using these specific modes. If they are using buses, if they are using cars, if they are using, I don't know, I mean, two-wheelers, whatever, you can integrate this in the multimodal MFDs. And then the simulation will give you a good estimate of the travel time. And then you can couple it with a choice model. And with this choice model, we have a good idea about the distribution of users among the system. And then you can build on that to do some optimizations, planning, control, whatever. But what you really need is then to have this good estimation of the speed of the users depending on the mode. And there, the multimodal MFD is very, very useful.
So MFD is one of the few things that in the traffic flow that started to go beyond traffic flow and started, as we discussed a little bit, going to control, even going to network modeling, into a lot of other applications. So you guys have done a lot of work in that. Do you want to talk a little bit about what you've done? I know you've done recently a lot of work on the ride-sharing side, but if there's anything that you guys want to start with, just go ahead.
Yeah, so on my side, again, I mean, my main application of the MFD is large-scale simulation. And with the large-scale simulation, you can address a lot of problems. And you're right. I mean, one of the main focus I had for the last couple of years is on-demand services, so e-hailing, ride-sharing, carpooling, and how we can improve. I mean, first understand how the system works when we start introducing this kind of services, and how the people will start using it. So it's more a mode choice problem, but it's very important to know how these new services will change the mode share in the urban area. But the most advanced application I did is really about the fleet management, how we can improve the fleet management and the rebalancing. And this is something we share with Nicolas, because we did a lot of work with different theory, but with the same kind of purpose, which is how we can improve the level of service through rebalancing, and also how we can optimize the sharing part of the system. And for example, I just want to give you that example, which for me it's super interesting. If you think at transportation system, and you start introducing ride sharing system, and you try to find what the optimal solutions, so the optimal solutions based on the demand, but you don't put any constraint about the number of sharing. And you start solving this with optimization method, whatever. What you will have in the end is a kind of optimal routing strategy for the vehicles you have, but you will also know what is the level of occupancy of these vehicles. So somehow, just by taking the problem very openly, you will have in the end what is the optimal distribution of vehicles with their different capacity you would need to fit the dynamic demands. So of course, I mean, because ride sharing means close origin destination, but also departure time. So it's quite a complex problem. But if you use, I mean, the MFD as the tools to represent the dynamic of the system, and then you start doing optimization, you can really design what would be an optimal service for a given city and a given demand pattern with the adequate type of vehicles. So it can be very advanced in terms of thinking the public transportations in the city. And you can even identify some bus lane, because you will see that there is some vehicles that are doing back and forth along quite a very regular routes where they have a lot of requests or share requests. And this is the bus line. So you can even think about using it. I didn't, but it's a possibility to redesign the complete bus line service based on the analysis of what would be the optimal sharing strategy at the city level.
So as part of that, you actually need to predict how the network is going to look like in the future. And that, there's traffic state estimation all of it happening as part of it. Because my understanding is you need to know where the demand is going to be so you can reroute everyone there or optimize your bus route, everything. Where is the boundary between simulation and traffic state prediction? Is there a boundary, or the same thing, we call them same thing, or we call them different thing?
I mean, for the application I mentioned, especially ride sharing and this kind of stuff, I mean, we don't really need to, because what we want to do is to just have an idea about the sizing of the fleet of vehicles and how they should operate. So it's the same network. And what is important is to have, for this application, is a good estimation of the travel time. So if there is congestion, this will increase the travel time. So the vehicles will not be able to, because a lot of this problem has been solved before without the MFD theory with static travel time. And the main issue there is that the availability of vehicles for next request is based on the fact that the travel time is right. And if you have congestion, the travel time is not right. So adding the MFD and MFD dynamics help you to have much accurate prediction of what the travel time would be depending on the operation of the systems, especially if you have a lot of vehicles. This will impact the travel time. And this is how you can really get something which is realistic in terms of optimization. For me, traffic states prediction is more when you do model predicting control in the system, and this is something I use, but more for perimeter control application, not really for on-demand services. But
yeah, I could add on this. So I believe when we talk about prediction, something important is the granularity of what we want to predict, and also the data we have available. So MFD models, they require only a small number of state variables to describe the dynamic of the systems, compared to detailed microscopic models like the one we have, for example, when we do detailed simulations. And in that case, predictions, I would say, are easier. But in the top of this, when we apply predictive control strategies, like model predictive control for perimeter control, there, even if your predictions are non-perfect, the system will operate well for two reasons. First of all, because you continuously monitor your states, so you have feedback. And second of all, because as you make aggregated decisions, like how much flow to allow to transfer from one region to another, what you care is more like the slope of congestion. So if you are in the uncongested or in the congested regime of the MFD, and towards which direction you move. So if your predictor can give you this direction, then you will do very well. While if you have a much more complex state representation with hundreds or thousands of state variables, even predicting this gradient might be too difficult. And also, when you need demand for this state dynamics, this demand also contains aggregated information, and for the two reasons I mentioned, also making some mistakes or some not perfect predictions there still might not be so dangerous for the quality of the control.
Okay, that's interesting. So you say you want to talk about another application of NFT. Can you talk about it now, or what is the other application?
What we haven't talked much is a little bit about the concept of the control. And if we look at control theory, not necessarily transportation, you have different type of approaches from fully centralized to fully decentralized, and then somewhere in between that we can call it distributed. So fully centralized approaches are expensive, both in terms of computation, but also depends on data needs. And there, also these approaches might be very sensitive to modeling errors, especially when we talk for networks with hundreds or thousands of intersections and many drivers that have to choose their route, passengers that have to decide their mode, their time of departure, and so on and so forth. So one option there that I believe MFD modeling offers is to have hierarchical control approaches that you have different layers, and maybe at the upper layer you use an MFD model to have an aggregated state representation. And by doing, I don't know, perimeter control or regional congestion pricing or redistribution of urban space or providing like dedicated bus lanes, you're able to bring the system in a better state and avoid being for critical regions of the city in the congested regime. And then the lower level comes, that the lower level doesn't need to be centralized. It can be distributed with small regional spatial information. And what we know even decentralized control approaches can do well if the system is not in highly congested situations. So you help the system to come in a better state, and then your lower level control can further improve. While if you ignore the upper layer and you try to do only fully centralized control with a very large number of decision variables, you have problems computationally in terms of modeling, but also data availability, because you need to estimate states that you don't have enough data to do. And this can really send you in a very dangerous condition for the system.
Okay, so how sensitive you are to data imbalance? I mean, so typically cities put their sensors where they think would matter most. That does not necessarily mean those are where would matter for your applications. How do you deal with that? Or that is maybe not even a problem?
So there, what I would say is that in the history of transport, I mean, cities have very experienced traffic engineers that have very good intuition. So usually they put sensors in proper locations to monitor congestion. But these are static sensors. And we also know that congestion has strong dynamic profiles. So if you want to monitor every link in a city, it will be too expensive. And what transportation researchers do for many, many years is to combine multi-sensor data. And there you have a variety of techniques, data-driven, most of them inspired by machine learning, etc., that they try to utilize multi-sensor data to estimate the state of the system. So this might be a good way to go. And as also cities experience different congestion patterns seasonally or over the years, by adding some type of moving sensors in the existing static sensors can really help. And as we all know, loop detectors are something that us as transport engineers use for years, but they also contain measurement errors and we cannot trust them a lot. They also fail and so on and so forth. But having also moving sensors, that this can be GPS from taxis, or in nowadays that maybe we can utilize drones with cameras that they just fly around and collect data. These approaches can really help us also to have data for areas that we didn't expect to be congested when we installed loop detectors. So it's difficult to say that we can come up with an ideal location of fixed sensors in the city, because maybe after 2 years, conditions have changed. Having this flexibility on how to monitor our cities can really help both the identification of congestion and also integrating this in different type of control strategies.
I fully agree with what Nicolas just said. I just want to, pinpoint a really specific problem in urban area, which is that traffic loops are usually implemented to handle traffic signals. because the main application is signal control, and they are usually very close to the end of the link, because what they want to know is when the queue is flush to basically balance the signals. And this introduces some bias when you want to capture the global dynamic of the congestion, because you basically observe congestion because you are very close to the queue generated by the traffic signal. This is why data fusion is very important, and this is why we are using a lot now probes, probe vehicles, probe informations, so I mean GPS, cell phone data, whatever, that represent the trips, because this gives us a better spatial coverage. Main issue here is the penetration rate, because every time we assume that we know the penetration rate, which we don't, and we assume that it is quite homogeneous, which is not, and this is where we really need to have some fixed measurements when we can make the correlation between the spatial information given by the probes and the quantity given by the loops. And I think that's the famous fishing method that Nicolas introduced in one of his original paper about counting how many probes are crossing some loops. It's very important to really connect the information we get from the probes and be able to scale them up to something that is useful at the network level.
So is the penetration rate the main reason that you decided to collect the data with the drones?
So look, this is more a data question and is not necessarily related to MFD modeling. So with respect to drone monitoring, what I would say is that fixed sensors, but also existing moving sensors, have pros and cons. And some of the cons is that loop detectors usually they don't provide high resolution data. They're at a single location. And you're not able to understand congestion interactions, especially in multimodal networks. So to give you an example, you have a taxi stopping in a location for some passengers to get in or out. It blocks a lane for 30 seconds. This might create some local phenomena. Similar might happen when a vehicle is cruising for parking. This local phenomena might have local effects and disappear after a few seconds. But if we're at close point to the breakdown, they can really propagate all over the system. This type of phenomena are difficult to observe with classical sensors. So drones give you the ability to monitor larger areas from the top and also have high quality data, because the accuracy you have in the trajectory is maybe errors of a few centimeters, and you have a full picture of the whole environment. And you can really understand vehicle-to-vehicle interactions. So understanding the effect that these local effects have at the network level is a very interesting and challenging question, and maybe these are one of the few sensors that can help you to answer these questions. And then this type of data can help us revisit, especially at the urban network, traffic models that researchers have studied since the beginning of traffic flow theory in the 30s, 40s, 50s, that also, to the best of my knowledge, these models in the 50s were the starting point of autonomous driving.
Yeah, pretty much. Yeah, it was the same time the idea was introduced.
No, I want to share one of my deepest thought about traffic flow theory, and it's about the NGSIM data. Because before NGSIM, I mean, if you look at the papers and how it evolves, you had so many different traffic models that have been proposed. So every year at TRB, you have a new bunch of traffic model, second order, third order, or whatever. And then the NGSIM data came out, and it was a revolution because we have a fine grain, even if it was only 300 meters and for one US freeway, of what was really happening during congestion with the stop-and-go pattern and everything. So we were able to basically compare our theory to something at a scale which make a real difference about which model were good, which model were very wrong, and especially what we have to look at. And I think that's what drones are proposing now, and especially, I mean, the first data set that Nicolas and his team has released for the Athens, city center of Athens. It's the urban NGSIM resolution, because now we know exactly what is happening in terms of all these multimodal interactions between the mode, all this double parking, all these capacity reductions that appear in the system. And now we can really, when we do traffic flow theory and traffic models, we can really look at if our model and our representations of the reality match with what we observe. And for that, we need fine-grained observations. And I think drone is a kind of unique opportunity to get a complete picture about what is really happening in terms of dynamics, multimodal dynamics in urban networks. And this is what we need to advance and also select among our traffic flow models which are the ones that are really adequate for the urban environment.
If I could add here, and if you let me change a little bit the direction.
Go ahead, yeah.
It's still about data, but I want to introduce a magic word which is called open science. And if we compare our field with other fields of engineering, we used to be, let's be honest, very much behind. So in the past, we didn't share data, and this made very difficult the reproducibility of the different models and the comparison between different forecasting techniques, etc. So these drone data we collected in Athens are publicly available. It's a fully open science. We're very close to release another larger experiment we did jointly with the group of Hwasu Yeo in South Korea, and this will also be fully open science. And we see that there are more and more efforts also in our domain for open data, open models, open codes. And I really believe that this can create breakthrough changes in our community and in our field, because we don't need to start from scratch, especially for our PhD students. So you start your PhD, you're excited about a topic, you investigate the literature, you see 100 papers, and if you want just to apply a few of these approaches, you need months. If each of us, every model we create, every database we use, we try to make it publicly available, I believe that really can help science and our field to further improve. And personally, I'm a big supporter of this. And clearly, NGSIM was the first point. And I believe still researchers today use NGSIM data, even if they are many years old.
Yeah, so one of the good thing about using NGSIM, and this is relevant to what I always like to see, is there's been a lot of studies with NGSIM, so it provides a very good comparison point, which do not exist for newer data sets. Which, now, this is the main reason I was talking about maybe we should create a benchmark, a blind data that no one has seen, and they just can introduce their models and then get the results out of it. So we can have like a sort of, let's say, car following, There's a set of trajectories that no one has seen. They just introduce their models in a specific format. We run it for them offline, and then we produce accuracy. That way we can compare different models, and that would be the benchmark for everyone to try to beat something. Like, okay, the IDM is at 90%, let's beat IDM, or whatever the model is. So, but I agree, these are very common in many fields, including CS, which we are now catching up. I'm very excited. So I have one. Do you want to add something?
Yeah, just a very minor comment, but you are mentioning computer science. Let's say image processing, which is a domain where open science is very well developed. But it's easy because they just need to have a bunch of images that are a reference, and then they have the algorithm open that they can train, and when the new algorithm arrive, we just compare the performances, and we know if it's improving. If we think about traffic, the first thing is that we have so many uncertainty of error measurement in the data sets. The data sets are not harmonized, so it's very difficult when you just move to another data set just to find where is my loop, where is my trajectory, where is my network, the math matching, everything that needs to be done before being able just to proceed the data. So, and then, indeed, we are not used to share our code, which is a pity because the benchmarks become difficult. But even when we share everything, and for example, during my ERC project, I tried to really follow this path, and what I've published is something like completely stupid in a sense. It's just audit trip pattern for the city of Lyon. So what you have is origin, destination, departure time. And this is a realistic OD matrix distributed over trips. But this took us a lot of time just to create that. And for people who want to use it, they have to understand the network. They have to be able to make some calculations. So we really need to have this kind of common pipeline that helps to handle with data uncertainty, data labelizations, network implementation, matching, and everything, so we can have a real common playground where we can test our algorithm.
Right. I have a few follow-up questions regarding the data collections. So one of the biggest questions that I always had looking at any sort of data set is, how did you pick those locations? Why those specific intersections? What was the motivation that made you, okay, these are the important ones? Because like Athens has a lot more intersections, obviously, but you pick a certain set of them. How do you do that? Like, what's the logic behind it?
So with a specific experiment in Athens, we tried to really pick up a downtown area that was about, if I'm not mistaken, 2 square kilometers. You have major roads, a lot of traffic lights, many interactions of cars and buses. So you try to choose a complex system. I would say that how you choose a location to do an experiment should be guided by what the cities want in terms of also improving mobility. So the Athens was an open science initiative that we just chose what we believed would be useful for traffic flow modeling in different type of data. But when we have data from different resources, this is usually guided by the implementation and what are the needs of an organization to do an applied project. What I would say actually is that we can use existing data, or maybe you can fly drones quickly all over the city to identify or use Google Map data to identify what are the critical locations, and then based on the potential application to zoom in and do more detailed experiments with an objective of improving mobility.
So you mentioned NGSIM and how NGSIM changed the way that we work in traffic flow. Before NGSIM, there's been a lot of simple, sophisticated models that was intended to capture the dynamics, like in some way observe. You mentioned a few examples of them. And since NGSIM and all the new data coming in, things are becoming a lot more data-driven, a lot more complex models are introduced. We're moving towards introducing like more complex deep learning-based approaches. Which one do you like more? Do you like the old school, simple, maybe physics-based models versus the data-driven models? Where do you see a role into the simplified data-driven, like simplified physics-based model that you used to work on quite a bit back in 80s and 90s versus what you're doing now? Do you still see there's value in doing that kind of work?
I entered transportation because I like unraveling mechanisms based on physical trial, building models, trying to see if they're able to reproduce the mechanisms. So I will not change my mind now, even if we have this very nice artificial intelligence things. I mean, for me, artificial intelligence has many very impressive applications, but they cannot tell you what is happening and why, because what they will tell you is what will happen based on their statistical analysis. So if you want to really understand what is happening, you need at one point to dig into the model and try to make some assumptions to understand what is going on. I mean, if you speak again of adjacent data and the stop and go wave and how they propagate and so on, I mean, data-driven approach will tell you there are shock wave, or will tell you the speed will be this level at this location, but it will not show you the wave that you can see when you plot these very nice trajectory pictures and see that it comes from one point and this is the generation of the wave and then it propagates. So I really feel that we need really both. And also, because you are mentioning philosophical questions, at one point there is another philosophical question, which is, do we still need transportation researcher? Because, I mean, computer scientists can do most of our applications with this, with all this method. But I think that transportation researcher know the mechanisms, know the physics of transportation, know what is happening, and this is how they can really adjust the methods that should be used and really ensure that what has been built has a real purpose in terms of transportation applications.
Can I add on this?
Yeah.
So I think this is not only philosophical. I think this is a factual question. And personally, I believe that AI can make us better scientists, but it also has the danger to make us lose our intuition. And this is where physics-based models play a significant role. We can understand and translate if our results make sense or not. So completely replacing transportation intuition for complex systems with black box methods that under proper training they can learn what you have observed, I believe is dangerous because you cannot predict everything perfectly, especially when the decisions we also make for mobility are multi-actor. So we don't have a central system with an operator that will make decisions for all different aspects of mobility. So you have public transport operators deciding for their system. You have traffic signal control operators trying to prove traffic lights. You have ride-hailing operators or taxi operators generating some fleets and distributing in the city to maximize their profit. The interactions between these subsystems are very important. And I'm not sure if you look in a subset of this problem, you can predict everything in a black box way. So I believe that ML techniques can help us, but they can also develop dangers and risks. And the other issue we might have in our domain is the blind implementation of vanilla ML methods. So we find some data online, we have a research question, we open an open science ML library, we get from there some code, we run it, we predict, we're happy. Maybe if we run 10 different models, one of them will give better results. Maybe if we train and we play with the parameters, we can do better. This is dangerous. So I believe that the two worlds should collaborate, and transportation researchers should become stronger in machine learning methods, and CS people, computer science people, should be able to create better intuition of the transportation problems. And this will make both disciplines better. And there we might open the door for education.
Yeah, I want to get to that. So
before, I just want to add something. I fully agree with what Nicola was saying, but I just want to be a little bit more provocative. The first thing I would ask is, show me big data in transportation. Because if you think about image processing, when you want to recognize dog and cats in image, you have a quantity of information in each picture, which is amazing. In transportation, there is no big data. Everyone's do big data analytics, big data methods, but on very scarce data sets in the end. And the only data sets that you can really think that it's close to what we have in other fields of computer science is, for example, time series. When you have loops and you have the flow every minute and you have large time series. But with that, what can you do? You can do traffic flow predictions. Who really needs to have very accurate prediction of the traffic flow in the next 15 minutes? Usually you take the previous data point and you replicate it, and it's already a good predictions. So there is not that much, currently applications of transportations where you really have a quantity of data that match the complexity of the problem you are looking at. And this is why physics-informed approaches make sense, because it's a way of providing a directions, even if you use machine learning techniques, a direction about where you have to look at, because otherwise, it's very difficult.
This is a big issue, and it will become worse, I guess, because I saw someone applying using maybe about few thousand data points to train train GPT-2, which has over 1 billion parameters, and you're not learning anything out of that, but you're producing very high accuracy for that very particular data because you're overfitting. But so it goes to that problem of education. How do you address this? What's your solution?
So personally, I cannot have a solution in the education per se, but we're faculty in different schools, and I believe we can try to influence the curricula we have. So I belong in the Department of Civil Engineering, and I'm part of the teaching committee for the next 10-15 years. So when I started at EPFL, I would say that bachelor students were in civil engineering, were not strong in programming, were not strong in optimization, were not strong in machine learning. Nowadays, all these three directions have more than one mandatory courses at the bachelor program. And bachelor students come in their year 3 to do a semester project with us, and you are impressed by their technical skills. So I believe that education should have similar dynamic features as research. We should update the courses we have in our programs, and we should be open-minded as researchers that even classical disciplines, they need strong fundamentals, but they also need to be updated with new tools, given that we have access to more data, stronger computers, and so on and so forth. So this is my 2 cents for education, and I believe that it applies in most of the engineering fields.
I mean, for me, there is one thing that will never change in education is the critical needs for critical thinking. I mean, being able to really take a step backwards and just think about the results we just got. And you were mentioning this this ChatGPT like model fit on a few data points. I mean, you need to understand that you can do this, but this doesn't make sense. And having this critical thinking, it's really fundamental to address any field of engineering, and obviously in transportation it's super important. And you have this famous sentence, I mean, all models are wrong, some are useful, but this is exactly what we need to provide to our students. The ability to look at some challenging issues, and we didn't mention the challenges that we have to face for transportation nowadays, but with climate change, I mean, the stakes are super high, much higher than it used to be some decades ago. And we need to think out of the box and really try to find holistic approaches, but also to have this sense of critical thinking about what we are proposing and how it's really fits with the challenge we have. And this is really something that we need to achieve through education.
So, from your experience of doing your research in this line of work, what do you think would be the next important problem that has not been looked into enough and can change the way that we look at the network level traffic flow?
So I wouldn't say that there is a $1 million question, but given the complexity of the transportation networks, better understanding the interactions of different modes and develop different type of control strategies for large-scale networks is clearly a key question, especially when you deal with different systems. So traditionally, we used to look at control for systems with cars and buses. Nowadays, we have a lot of on-demand transportation. You have last-mile deliveries and logistics services in the system. Trying to understand at the network level how to monitor, model, and control mobility for all these systems by putting emphasis on humans and not on vehicles, I believe is an open area that all of us can make many contributions. And you can see this from many, many different angles, and you can define many sub-problems that are all still also very interesting and challenging.
My focus has always been urban transportation system. And if you see what's happened over the last 10 years, I mean, we introduced a lot of new technologies, new services, more stakeholders, because now you have private actors, public authorities, a lot of people trying to propose solutions. So you have communication, you have many things, but the space is the same. So basically, we took this, and for the last 10 years, we were bringing new options, new solutions. So on-demand services, carpooling, new bus, bike lanes. So we are basically just like adding layers to layers to layers. And I think that's now what is really the challenge, is to make everything work together. So it's about the cooperation between all the modes of transportation, all the services, all the options that are provided. But also having a sense of sharing, because in the end, we have limited resources. And we know that mobility has some environmental impacts. So, and we know that some modes have a lower carbon footprint than others. So if we start thinking of all this, you can quickly come to the conclusion that we cannot have everyone take the options with the higher carbon footprints just because they like it the most. So there is a real question about how the system will be designed, what will be the regulation, and how we can basically balance the crucial need for mobility, which is out of the question, with the impact, and how we can make this work smoothly together. And for me, this is, we have many pieces of the solution, but trying to assemble these pieces all together and having basically unlock the mobility puzzle is the new challenge for transportation.
Yep, thank you so much. I know we're waiting for you. Appreciate it.
Now, if I may, just a personal comment, and for this podcast, and because you are speaking a lot about new PhD students in transportations, and I would like to share my experience about the transportation community. And I think we have one of the friendliest community in research on many fields, and this is also because transportation is not that big. And what I really like when I was a PhD student is that it was quite easy to approach the famous professors, discuss with them, discuss with the teams, connect. And we have all these very nice events like this conference, which is in the end a small scale conference. It's only 200 people. We can discuss with everyone. We have TRB committee where, again, we have this small, I'm used to speak about transportation family, and somehow this is really something I like with the transportation research, is that you can see this as a big family. There is not that much conflict, there is not that much kind of search of some theory or something like that, people defending. There are some argumentation, there are some debates, which is good, but in the end, everyone is really respectful of the other opinions, and this is what I like with this community. And I think this is why I say, if you have to choose a field of application for your PhD, do transportation.
I couldn't agree more. I experienced that firsthand. Yeah. Thank you.
Thank you, Ali, for having us
Thank
here.
you. This was very nice.